All right. The Unscented Kalman filter. I'm really happy that we're able to cover this. I'm able to teach you about the Unscented Kalman filter, in part because one of the people who's done seminal work in developing the theory of the Unscented Kalman filter is right here at Portland State. Eric Wan, who taught a course last fall that many of you took, has published some of the critical papers on the Unscented Kalman filter. If you look on the citations on the Unscented Kalman filter, he has a few publications, or at least one that's been cited over 1,000 times, which is like amazing. So, so it's really great that we have him here. If you have questions about the Unscented Kalman filter, I'd almost say go talk to him, because he knows it better than I do. But here's just an overview of what we'll be covering. For Tuesday, I'll try to add another example. Walt had requested earlier that we look at what the Kalman filter does with card tracking, and I couldn't because it's nonlinear, and the Kalman filter only works in the linear case. But we can do that with the Unscented Kalman filter. So looking at how it behaves for a problem that is multimodal would probably be interesting. And it's not that hard for me to do, so I'll try to add that in time for Tuesday. Okay, so we've in this class we've already talked about a few other techniques, and I just want to explain a little bit about how they relate to one another. I think I've already said this enough times that you know, but just to say it again, particle filters work for very general nonlinear systems. You can have nonlinear interactions with a noise. There's a lot of great things about particle filters. You can look at the distributions. It can handle the multimodal case, which is really key. But there's a critical weakness, which unfortunately with the homework assignments I didn't push you guys probably hard enough to really run into, which is that when you have a high dimensional state space, you need one heck of a lot of particles in order to track well. And you can lose track of modes because when you resample, all the particles can end up just tracking one mode. So I kind of wish I would have made you guys work on a state in a very high dimensional state space also, just so you could see that limitation of the particle filters. I mean, you can overcome it if you throw enough particles at the problem and you're clever, but it's kind of a pain that is a good pain to experience. You know that there's good reason to avoid it, and you're not just lazy and you throw a particle filter at everything because you're like, it's the most general tool. So there's a curse of dimensionality that you can run into with particle filters that I think most of you are in a low enough dimensional space that you just didn't run into. The Unscented Kalman filter, the key advantage it has over particle filters is that it's way, way, way more efficient computationally. For those of you that are working on real-time applications, this is probably a far better tool than particle filters, especially if you've got a unimodal posterior. In the applications that I've worked on for both my research and with companies, the Unscented Kalman filter is usually my go-to algorithm. Unless there's strong reason to believe there's a particle filter is needed, this is what I almost always use, because I'm always working with nonlinear things, but the Unscented Kalman filter is what I usually use. There have been a few exceptions, but it's usually the Unscented Kalman filter. The Unscented Kalman filter is based on the Kalman filter recursions, but it's got to linearize the nonlinear model. And because it's based on those recursions, just like the Kalman filter, it's only tracking the mean and the covariance of the state error, or the covariance of the posterior, if you want to think of it that way. So it's only tracking those things. We can't see more than one mode. It's just tracking those properties of the distribution, just like the Kalman filter does. And then the extended Kalman filter was developed very shortly after Kalman published a seminal paper on the Kalman filter. People started immediately thinking about how to apply this to nonlinear systems. And so I think it was the early 70s, the papers were published essentially describing the so-called extended Kalman filter. And so this has been used for years and years and years. The Unscented Kalman filter was first published, I think, in '95. But it really didn't catch on until about 2000 or early this century. And particle filters, followed like basically a decade after the Unscented Kalman filter. So in the history of these state space tracking methods, the extended Kalman filter has been around much longer, And so a lot of people have used it, and because a lot of people have used it, a lot of people continue using it. A lot of people go back to it. They're like, well, I read all these papers, and the senior engineers, and they're all using the extended Kalman filter, so of course I'm going to use the extended Kalman filter. But I hope none of you ever use it. It's based on a first-order Taylor series approximation of the state space model. You can see one of the things I have here is additive noise. Implicitly, both the extended Kalman filter and the unscented Kalman filter can handle nonlinear process and measurement models, but they both more or less are based on additive noise. At least that's the way they're developed. The book does describe a way in which you can account for cases where there's a nonlinear interactions with the noise, where you essentially fold the noise into the state vector and treat it as part of the state. But usually people are applying this to a case where you've got additive noise. So it's based on basically calculating the equivalent of derivatives or Jacobians of the process model and the measurement models, and linearizing about your best estimate of the state. And there's tricks you can do to make it a little bit better. But as I'll show you an example of, these local linear approximations can be really inaccurate. If you're around the point of a strong nonlinearity, then these estimates can just, they can be really bad, and it can be really hard to tune because how you tune it depends on how good your linear model is, which can change depending on where your state happens to be. And so there's a lot of problems associated with it. The reason that I'm teaching you about the Unscented Kalman filter and that I'm not covering the extended Kalman filter is because, as far as I know, the three tools that we focused on in this class, the Unscented Kalman filter, particle filters, and the Kalman filter, if you've got those three in your toolbox, you're set. For any application where someone would apply the extended Kalman filter, you're almost always, you could find a very weird edge case, but I've never quite seen one, and Dr. Wan has said exactly the same thing. The Unscented Kalman filter almost always beats the extended Kalman filter. You'd be very hard-pressed to come up with an application where the extended Kalman filter is a better choice. Again, you could probably find an edge case, but it would be very, very unusual. So the Unscented Kalman filter is a great tool. And it's kind of an intermediate between the Kalman filter, which requires linearity, and particle filters, which are very general but computation heavy. It kind of sits in between those two extremes. It's a really good go-to state space tracker. And it's appropriate for a lot of the applications you guys have been working on in your homework, again, because a lot of you have seen the posteriors for your models have turned out to be unimodal. And so tracking the mean and the covariance would characterize things very well in a lot of those applications. Yeah? Okay. So hopefully you're suitably motivated to learn about this thing called the Unscented Kalman filter. So the model I'll be using is more or less the described here. I didn't add in all the equations about the noise covariance and the noise being white noise for both the process noise and the measurement noise, and knowing about the initial state. But all those things you learned with the Kalman filter apply for the Unscented Kalman filter as well. The tricky part is, how do we deal with the fact that we've got these nonlinear models? And the things that we're going to be trying to estimate are the mean of the state, the covariance of the estimate, and the mean of the measurement. This is a little bit weird. I should have said the prediction of the measurement and the covariance of that difference. So these are essentially the same things we did with the Kalman filter. In the linear case, this was straightforward. This is kind of a high-level summary of how we answered those 4 questions for the Kalman filter. Estimating how this moved ahead in time doing the prediction step turned out to be relatively straightforward because we had an estimate of time in, and it turned out we could just, because this is a linear operation, when we take the expected value, the process matrix could be pulled out of this integral where we do the expectation, and it ended up being really easy to do a prediction of what the state is going to be. Similarly, it ended up to being really easy to predict what the measurement is going to be, because we take our predicted value of the state, its expected value, and just multiply it by the measurement matrix. So those turned out to be really relatively straightforward and easy things to do. But those things are very hard to do when it's nonlinear, even if you're just interested in the mean. And the main reason, and the conceptual mistake that a lot of people make, is that with a linear model, when we've got a linear operation, we've basically got a matrix times a random vector, the expected value of that product, we can interchange order these operations, because doing expectation and doing a matrix multiplication are both linear. And when they're linear, you can change the order. You know, if I wrote this out as an integral, and you basically have a product inside an integral with a constant, we can move the integral inside, since this isn't a function of the variable of integration. And so we end up with just the matrix times the expected value of that random vector. It's straightforward. But it doesn't work when you've got a nonlinear function. We say, well, what's the expected value of y, where it's some nonlinear function of this random vector x? This is not, in general, it's not simply the nonlinear function of the expected value of x. And that's important. You know, it's kind of a good question for the final quiz, because this is something that you should know as graduate students who are going to be getting at least a master's degree. So, for example, in the scalar case, if x is, let's say, just a normal, drawn from a normal distribution, and let's say y is equal to x squared, this makes it easy, because we know the expected value of x squared is going to be the variance, which, you know, is just a property of the distribution. So we know that's true, but the expected value of x is given as 0. And if we plug that in and take the squared value of the expected value of x, we get 0. Completely different, right? So in general, the expected value of a nonlinear function of a random vector or random variable is not the same as that nonlinear function of the expected value. Is that clear? It's one of those important ideas that I hope you've seen before. Okay, so let's briefly look at what would happen in the extended Kalman filter framework, where you're basically working with a first-order Taylor series approximation of these nonlinearities. That's what the extended Kalman filter is based on. And right now, this is simpler, where we're simply talking about, I guess I don't quite have the equation here, but we're talking about a random vector y is equal to some nonlinear function of a random vector x. And I haven't incorporated time in here, or this isn't necessarily the measurement model. This is just more generally when we've got a random vector, a nonlinear function, and the nonlinear function of that random vector is what I'm calling y, some other random variable. So if we did linearization, then y would be equal to h at whatever value we're evaluating this at. H of some value x naught times or plus the derivative times the difference between at what value we want to generate the estimate and the point at which we're doing the linearization. This is just Taylor series approximation. The book formulates this a little bit differently, but it's equivalent. And so if we apply that to this very simple nonlinearity, in our case, and we say, well, we want to evaluate this at the expected value of x, where we know what the mean is of that random vector, then we end up with this expression. And if you evaluate that for x naught is equal to 0, then once again we end up with an estimate of being 0, where we know truly, since we're taking the expected value of the square of a normally distributed random variable, it should have been just the variance of whatever that distribution is. But when you do this linearization about a value of 0, you get 0. You get something that's completely wrong. And if we'd linearized about x0 is equal to 1, we actually even end up with a negative value, even though y clearly has to be non-negative. So that starts to give you an idea of some of the hazards of using a Taylor series approximation like the extended Kalman filter is based on. So this is why that type of linearization is a bad idea in general. Although, for what it's worth, it can be good. I'm disparaging it too much and not giving enough credit to the 30 some odd years that the extended Kalman filter was kind of king when it came to nonlinear state space tracking. in our case, we've got something that looks kind of like this, where this is x and this is y. This is our nonlinear function of x. And one of the things, maybe just to say a little bit more about this, about, well, if it's that bad, why did the extended Kalman filter ever work? And part of the answer is, well, it depends on how much uncertainty you have in your state estimate. If we build this linearization model, and let's say it looks something like this, over a narrow range, let's see if I can do this here. So we're linearizing about this point. This would be x naught in this particular example. So in this case, if the variation in x is very tight, then that linearization may be quite accurate. But if we've got a lot of variation in x naught, then it can be very inaccurate. So it depends partly on whether there's enough variation in your state that you're really kind of exercising the nonlinear range, or whether it's tight enough that a local linear approximation is pretty good. And in the applications where the extended Kalman filters worked well, it's almost always been in these cases where, yes, it's nonlinear, but given how well you're tracking, there's not enough variability that the nonlinearity departs significantly from a linear approximation at that value of the state. So it can work well, it just depends. But again, the Unscented Kalman filter works well in both cases. So these days, I don't know why anyone would use an extended Kalman filter. You guys with me so far? Is this okay? Okay.
Maybe it'll be unclear later, but why is it called unscented?
Yeah, that's a good question. And it took a while for people to settle on what this was going to be called, and actually Dr. Wan was carrying the banner to have this called sigma point Kalman filter. That's what he wanted it to be called, and so there have been different terms that have been used for this, and I believe one of the transformations that they do, they called it an unscented transformation, I think, because there's something kind of like whitening. So they're kind of removing the scent, I think, was the idea. I think that's where that term came from. But there's an unscented transform was the term they used to call it. But if you see sigma point Kalman filter, it's essentially the same thing. And Dr. Wan would probably say, oh, well, the unscented Kalman filter is just one special case of a broader class of methods called sigma point methods. But terminology doesn't matter a whole lot because almost everyone uses the same set of basic recursions that I'll be going over shortly.
The Wikipedia page says it was called unscented because the guy was trying to come up with a name and saw a stick of unscented deodorant.
That's a better story than mine.
Story.
Okay.
Maybe anyone can edit Wikipedia.
Nice.
You never know.
I'll bet he'll know. He'll know. He'll know the answer better than me. Maybe I was wrong. All right. So what do we do, or what did the folks that come up with this? What exactly did they do to overcome this? In general, if you're thinking about an entire PDF, it's really difficult to figure out how PDF sort of morphs when you put it through a nonlinearity. Regardless, in our case, we've got two nonlinearities that we need to worry about, both the process model and the measurement model. And when you take a random vector and you put it through a nonlinearity, even if you know what the PDF is, and even if you know what this nonlinearity is, in general, that's a mess. It's really hard to say what's the resulting PDF of this thing, of this random vector after it's gone through this nonlinearity. That's a hard thing. Particle filters finesse that by saying, well, we're going to push a bunch of impulses through there and represent the PDF as impulses. It's very, very clever, very strange, but it's very effective in practice. But theoretically, at least, that's kind of a hard thing to do. The extended Kalman filter, as I said, just linearizes the model and says everything's good. We're just going to keep everything Gaussian and just pretend that this is actually linear, or more specifically, I should say affine, since it's a first-order Taylor series approximation. But again, that has limitations that I explained in the earlier slide. So the unscented transform is based on a couple of key ideas. The first thing is we can easily put points through these models. We know what they are, and for any given value of the state vector, we can push that through and compute that really quickly. The particle filters leverage that same property, that we know what these nonlinearities are, and we can calculate it for a point. The second thing is that we can, it turns out, fairly easily create a set of points that adequately models or captures the mean and the covariance. And this is different than particle filters because we're only thinking about the first and second moments of the distribution. We're not worried about trying to model the entire PDF the way particle filters are. In this case, we're trying to be more efficient, and we're only caring about the mean and the covariance of the state error. So we're aiming for less, and it's possible to find a set of points that have basically the same sample mean and covariance as what it is that we're trying to model. So we can create a set of points that kind of represents a distribution or has the same sample properties as the distribution. I haven't shown you how to do that yet, but we can do it, and I'll show you how shortly. So basically the idea is if we know the mean of the state and its covariance, so we start off with that information, we can find a set of points that represents that, and those are the so-called sigma points. Then we can apply our nonlinear function, and we've got two of them, so we'll have two nonlinear functions we can apply to each of those points. And then the sample mean and covariance of what comes out of that, we apply each of the points individually to the nonlinearity. We get out something for every one of those sigma points. If we have enough of them, we can calculate the sample covariance and the sample mean, and there'll be a pretty good estimate of what the true mean and covariance are. So that's the magic of sigma points, or the Unscented Kalman filter. I'll show you how to do this. So here it is. It's again, we're starting off assuming that for the input random vector that we know what its mean is and we know what its covariance is. And I've added the time index now because we're getting closer to folding this into a filter. And I'm not specifying right now whether x hat of n and the covariance matrix, whether those are the filtered or the predicted estimates. It turns out we'll use both of them, but I'm going to be vague right now on purpose so I don't have to repeat this for both of them because the idea is the same. The way the sigma points are usually chosen, there's other ways of choosing it. The book describes some alternate formulations, but this is the most common way, and this works really well. It's usually the most accurate, is to take your mean, and then you kind of tweak outside the mean. You add a kind of a delta to your mean, and these perturbations, this tilde no longer indicates the difference between the true state and the estimate, and you can see it's not boldface, but instead this is calculated from rows of the square root of your covariance matrix. And I know some of you probably don't know how to take the square root of a matrix, but I'll explain that in a minute. Turns out there's a bunch of ways to do it. But yeah, or you can just say, MATLAB, take care of it for me. But we take the square root of the dimension of your state vector times the state error covariance matrix. You get a square root of that matrix, and then you get all the different rows. And every time you pull off a row, and that becomes one of the kind of deltas, one of the ways that you calculate a sigma point by perturbing the mean, you also do the same with a negative. So if I had to sketch out kind of a diagram of what this looked like in two dimensions, so this is maybe xn along the first dimension, this is xn along the second dimension, and let's say that your mean is right here, and then maybe you've got a covariance where that would represent something like a 95% confidence interval on the covariance of your state vector. Then basically your sigma points would be a set of points. I don't think that it would be along the major and minor axes of the ellipse, but it might look something conceptually like this, where you would end up with a set of 4 points where the sample average of those 4 points would be the same as where the mean is of your state. And if you take the sample covariance of those 4 points it would match exactly your state error covariance matrix. So, as a mental picture, I think that's a pretty good cartoon of what's going on and how it represents the mean and the covariance is a set of points. You guys with me okay? All right, so a square root of a matrix is any matrix that satisfies this property. When you take the square root transpose times the matrix, you get the times the square root, you get it back. And I'll say more about that in just a minute. One thing that may be a little bit confusing because we spent so much time talking about particle filters is, are these sigma points? Well, how are these really different than particles? It doesn't seem like they're that different, maybe. But there's some big differences. One of the differences is that the particles were drawn from a random distribution. They were drawn from the importance density that you as engineers chose. And most of you chose the process model as your importance density, but you could have made other decisions. Some of you tried some other things and found they didn't work so well, and some of you tried some other things still and found they worked better. But in any case, it came from the importance density. These sigma points are random. The book says they're deterministic, but really they aren't, because the sigma points depend on the estimates of your state, and those estimates depend on your measurements, which are random. And so this is a random vector. The sigma points are random vectors, but you're not drawing them from a random distribution. As soon as you've got an estimate of your state, and you know what your state covariance is, and the state covariance isn't calculated exactly in this framework, unlike the Kalman filter, that you've got an estimate of your state covariance. But once you have those two, once you have this and this, then the process for calculating your sigma points is deterministic. You're taking the square root of a matrix and then adding the rows, the positive and negative versions of the rows, to the estimate of your state to generate these sigma points. And there's always exactly 2nx of them. So whatever the dimension is of your state vector, you multiply that by 2, and you're always working with that many sigma points. So in those respects, it's completely different than particle filters. Yes, they are points. Yes, we're representing properties of a distribution with those points. But we're only representing the mean and the covariance, and 2nx is ample for representing that. You can actually do it with less if you wanted to. There's no random number generators involved when you're working with the Unscented Kalman filter, which is a bonus in my book. Those particle filters, that still bugs me that you need a random number generator to create the estimates. So those are the differences as compared to particle filters. Clear? Okay. So we need to take the square root of a covariance matrix in order to compute these sigma points. And very briefly, for those of you that haven't worked with square roots of matrices before, a matrix square root, this language is a instead of the, because there's more than one. A matrix square root is any matrix, and I'm denoting it as the square root of A. It's any matrix that satisfies this property. And you can see pretty easily that there's more than one, because let's assume right now that the square root of A is a matrix square root of the matrix A, and let Q be any orthonormal matrix. Orthonormal means that if you multiply the transpose of Q times itself, you get the identity matrix. If I've got a square root and I multiply it by Q, that will also be a matrix square root. And one way of thinking of an orthonormal matrix, it doesn't change the size of a matrix or vector that's multiplied by. So you can think of this as almost a rotation. So you could do almost any random rotation of the square root of a matrix, and it's also a square root. So there's more than one. There's an infinite number of square roots of any given matrix. You can use any of them. I mean, it kind of doesn't matter what you use, but there's a common choice in our context, because we have not just an arbitrary matrix, but we have one that is positive definite and is symmetric. And that makes the choice a little bit easier from a computational standpoint. So some of you may not know, I don't think I've really emphasized it earlier, but for those of you that don't know what a positive definite matrix is, a positive definite square matrix, it's any matrix that meets, it turns out these two criteria are equivalent, so it doesn't have to meet both of these. Either one of those is sufficient for it to be a positive definite matrix. So if all the eigenvalues are positive, it's positive definite. If it satisfies this property, that for any vector x, any vector at all, that if you sort of take a matrix inner product where you sandwich this in between taking the transpose of the inner product of the vector with itself, if that's always greater than 0 for any vector x, then it's also positive definite. It turns out that, well, I won't go into it. There are some other really cool, interesting properties that relate to power spectral density, but I'll spare you for now because it's not relevant to this.
What is the second condition? That greater than 0, that's like not each element of the resulting? Or does it always end up, that ends up just in a number? Sorry.
Yeah, this is scalar
Yeah, it's gonna,
because x is a vector. Yeah, so that whole thing ends up being a scalar, and if it's always positive for any, I should have said non-zero vector, I hope that was clear, but any non-zero vector x, then it's positive definite. And if you happen to have a symmetric positive definite matrix, then the Koleski, I think that's how you say that, factorization, produces an upper triangular matrix that satisfies the square root property. And this is a pretty efficient algorithm. And it's quite stable numerically. You don't tend to have quantization problems with this algorithm. It requires nx cubed over 6 arithmetic operations, multiplications and subtractions, and it requires nx square roots. So it's pretty dang efficient as algorithms go for calculating the square root of a matrix. I don't know why you'd use anything else. In MATLAB, this is col, and in Python, it's apparently given by that. I haven't used it, but I looked it up. And it's a really convenient way to calculate a square root for the type of matrices that we're working with. Yeah? All right. Do you guys want a break? Okay. Let's take 5 minutes, and we'll come back. Do you guys have any questions? No? It's clear? Easy? All right, so as I mentioned, these are the sigma points, same equations we had before, where again you take your estimate of the mean that we get from the recursions, and your state error covariance, take the square root, calculate the rows, add positive and negative versions of each row to get each of your sigma points. And these are chosen carefully so that if you take the sample average, you get your mean of the state back. This is relatively straightforward since for every positive thing you add a negative equivalent. So those all cancel out when you're taking the average. And if we calculate this sample average estimate of the covariance, they're chosen so that this also works out to be the same noise covariance. So they were chosen specifically to have those properties. And the way we estimate now, coming back to our problem of we've got some nonlinear function, a random vector going through a nonlinear function, how do we figure out a reasonable estimate of the mean of the output of that nonlinear function and its covariance? We take each of our sigma points and run it through that nonlinear function, and we get these, I don't have a name for these, but in this case we would get the output for every one of those sigma points. We take the sample average, and we get an estimate of the mean, and we take the sample average of the outer products, and we get an estimate of the covariance. The U is just a mnemonic to indicate that it's the unscented estimate, as opposed to the other estimates that we've talked about. So that's how we use it to get through that nonlinearity and address that question. It's quite different than the Jacobians and the Taylor series approximations that the EKF is based on. I mentioned I had one small gripe with the text. I think overall it does a great job explaining how these transformations work. It may not explain why they were called unscented, but it at least explains how they work quite well. And I think it gives a really nice treatment of the Unscented Kalman filter with some really good examples that complement what I'm doing here. But I think they got one thing wrong, which is they argue that the mean of the estimate coming out is accurate up to third order. But if you look carefully, and they say linearization, the extended Kalman filter is only accurate up to first order, and that's why this is so much better, because it's accurate with up to a higher order. In your Taylor series approximation terms, this captures the second and third order statistics more accurately, whereas the extended Kalman filter only covers it up to the first order approximation. But all of that math is based on the assumption that you know exactly what the mean and the covariance are of the state. And in general, when you're applying these recursions, you don't. You only ever have estimates of the mean and the covariance. So I think that claim doesn't really hold in our context when you're applying the Unscented Kalman filter. So I don't think that's right. I think that's one point where the author was overstepping and claiming too much in terms of the accuracy of the Unscented Kalman filter. But nonetheless, I think this is better. It's way better. It's especially better than back before we had symbolic solvers. And I think I mentioned this once before, but there was a time when a lot of engineers spent their times calculating all these partial derivatives, calculating these Jacobians by hand. And oh my gosh, that was very error-prone, very tedious, and took a long time. I mean, there are engineers that spent, I think there are some that spent over a year like trying to get through and make sure every last element of all their Jacobians are right so they can apply the extended Kalman filter. And you don't need any of that. There's no Jacobians necessary with the Unscented Kalman filter. So that's really nice. Although these days with the symbolic solvers, it would be less of an issue though. You could actually do it fairly easily, even in very complicated cases. But it also just seems to be more accurate because it accounts for the nonlinearity in a more accurate way by pushing actual points through the nonlinearity rather than relying on that local linear approximation. So the main thing is it seems to be much more accurate, and the order of the computation is the same. There is an expensive step that is order n cubed, or I should say nx cubed, but you have that anyway in the Kalman filter recursion, so you have that with both of them. The way the computation scales with the dimension of the state vector is the same. So computationally, there really isn't much of an edge for the EKF. So this is just a recap of using sigma points to estimate the main properties that we need. Otherwise, the recursions are essentially the same as the Kalman filter. So it works even though we've got a nonlinear system. I really don't think you can claim any type of optimality, but I don't think you can claim that with an extended Kalman filter either. There's always hand-waving about, well, it's optimal if your linear approximation is perfect, but if that was the case, then you'd be using the Kalman filter in the first place. Then it's not nonlinear. So I don't think there's really anything you can say about optimality, but these work very well.
So with a particle filter, your measurement model, you don't need to have a closed form h of n expression for it, right? You just need some way of getting a measurement based on some states.
I think I know what you're getting at, because sometimes this may be a black box where you can't write it out in terms of explicit equations. And it's true for both the Unscented Kalman filter and for particle filters that these nonlinear functions could be black boxes. You don't have to have an explicit mathematical equation that you can write for what those are. You do need that for the extended because you've got to calculate those Jacobians. There are ways of approximating the Jacobians, but then you're almost back to doing the Unscented Kalman filter.
Sorry, yeah, I was confused about something.
It's okay?
That's a good point, though. Because you can do, those functions can kind of be anything, right? Piecewise or otherwise you don't necessarily
Yeah, that's right.
something like that. I mean, you could put, if then else type stuff there, or have whatever sort of crazy.
Yeah, you could be pretty crazy, but I guess one small note of caution is to recognize that we're still assuming that the posterior is unimodal, and that and there is still kind of a statistical linearization that we're doing of these nonlinear functions by pushing the sigma points through them. We're still taking mean and covariance and then figuring out what the mean and the covariance is of the output. So if you've got really nasty nonlinearities with discontinuities in them, then I would probably be more inclined to at least start with a particle filter and see whether there's any evidence that there is that it's multimodal. You do have the same problems also with having constraints on the state vector, whether they're strict equalities or inequalities. Like the discussion we were having with Aaron. Same thing applies here. One of the things I personally struggled with Unscented Kalman filter is how do I account for cases where I know the state can't be any larger than a certain value, or elements of the state vector is within certain bounds. That can be hard to enforce. You may be able to enforce that in your process model, but what the filter does in creating estimates of the state, there's no obvious way to constrain it so that estimates of the state are within certain bounds. With particle filters, it's trivial. So there's still some limitations, but it is true that you don't need an explicit mathematical expression for HN or FN. Those could be what I'll call black boxes. Time varying, dimension varying over time, all that good stuff. So here's the UKF. With most of the algorithms that we've talked about this term, I've been able to get the entire algorithm on one slide, but I couldn't do it with the UKF, so it's going to be 3 slides, I think, is what it took. But these steps are relatively straightforward, I think. As before, we've got to start off by having some kind of idea of what the mean of the state is before we have any measurements, just to initialize it, and some expression of how much uncertainty we have. And I'm using slightly different notation as I describe the algorithm, because there's a few different covariance matrices that we have to keep track of. And so I'm using P to indicate that we're dealing with a covariance matrix, and then I've got an additional subscript that indicates what it is the covariance of. So, and I'm sorry, I'm overloading their notation here. This X tilde doesn't mean the perturbation of the mean, but rather the state error covariance matrix. So this is just the state error covariance matrix, and this is at time 0, and it's the filtered version after the measurement update. So that's what that is. And as I said, the way we create the sigma points is we take the square root of that matrix, multiply by nx, grab the different rows, and perturb our best estimate of the state to get the sigma points. Once you have the sigma points, to do the time update step, or what is sometimes called the prediction step, we take each one of those sigma points and we run them through our process model. Once we have that, we calculate the sample average of the outputs to get our estimate, our predicted estimate of what the state's going to be. That's our predicted estimate of the state. And we similarly take basically a sample average of the difference between our outputs and their sample average to get an estimate of the predicted state error covariance matrix. Yeah, so remember there's the prediction step where we're making predictions. This gives us a predicted value of the state, and this gives us the error covariance of that prediction. Very similar to the Kalman filter in terms of what it's producing, but the way it calculates it obviously is different. And then there's this other step that is called the sigma point update. And this can be a little confusing, in part because it's not super important. It turns out you can skip this step altogether. But after we take our sigma points and we push them through that nonlinearity, what we're left with are not technically sigma points in the sense that they're not computed quite the same. We didn't calculate these by taking our predicted state error covariance, but we can correct for that now and get the sigma points from our estimate. So we go through the process of creating another set of sigma points based on the estimates we just produced of the covariance matrix and the mean. Or we can just use those sigma points that came through that nonlinearity and save ourselves a little bit of computation, but maybe at the expense of accuracy. So whether you do this kind of little bit of cleanup so that you've got real sigma points that have all the right properties or not doesn't matter that much, but it can be a little more accurate. And then the measurement update, I think this is the final step, where we take account of our measurements, is done this way. First of all, we take the sigma points from the step where we just created them. So we've got our, I should have made it clear, this is the predicted estimates, the sigma points that are from the predictions, and run them through our measurement model now to get the, I don't have a name for these, but kind of the measurement sigma points, if you will. And then our predicted value of the measurement is just the sample average of those points. So we take our sigma points, run them through this nonlinearity, calculate the sample average, and that gives us our predicted estimate of the measurements. And from that, you can calculate your innovations. As soon as you have this, you can take the difference between your actual measurement and that, and you've got your innovations that you can use for tuning and diagnosis. We also use these to calculate the covariance of our predicted measurements. So this is the difference between, oh, I said that wrong, I'm sorry. This is the difference between the measurement sigma points and the average. So it's that covariance. This is not of the innovations. And then there's another matrix that we compute that is different than the common filter recursions. This is a slight difference where we're getting a covariance matrix. And this is a sample average of the state sigma points minus their average times the transpose of the measurement sigma points minus their average. And that gives us an estimate of that covariance matrix. So this is P and X tilde, Y tilde. And then the common gain is that covariance times the inverse of the measurement matrix. And then we update the estimate of our predicted state estimate in the usual way with the common gain by multiplying it by the innovation, the difference between what the measurement actually was and our best estimate of it. So then we get that estimate, and the way the filtered state error covariance matrix is computed is as the predicted minus, and this is just an alternative formulation of the common filter recursions, but minus the common gain times the predicted measurement covariance matrix times the transpose of the common gain. And that's it. That's the Unscented Kalman filter. I know that took 3 slides, but that's it. Do you guys have any questions, or are you ready for an example?
Yeah, I need to see this in action.
All right, let's see what it does.
Would it be kind of correct to think of sigma points as, so with a particle filter, you have these particles that are approximating the prior and then the posterior. It seems like sigma points are kind of particles that approximate the likelihood?
No. Sorry. Particle filters are an approximation of the marginal posterior, but they're only trying to approximate the mean and the covariance. So they're not really characterizing the whole distribution, but to the extent that it can be modeled as by its mean and covariance, that's what they're really capturing. But it's the marginal posterior, the mean and covariance of the marginal posterior is what the sigma points are representing. And there's not an analog with particle filters. I'm sorry, with the particles that are used in particle filters.
You mentioned that typically we take twice the number of states as the number of sigma points. and it can be fewer in some cases.
Yeah, I didn't go through it here, but if you look in the last sections of the book on the Unscented Kalman filter, it talks about some alternative ways of choosing sigma points that are computationally more efficient, where you don't need twice the state dimension. It turns out there's a way that you can essentially cut it in half, but you do it at the expense of accuracy. And they show an example, and they have 3 different algorithms and 3 different ways basically of picking the sigma points. So you can do it with fewer, but it's often less accurate than the algorithm I described here.
Okay. And if I just pick them randomly, would I need like an order of magnitude more number of points for the same accuracy?
Don't pick them randomly. Gosh, if you're going to pick them randomly, you'd want to pick them so that the ensemble mean matched the mean and the covariance matched it, and you would need a lot more. And I don't know what you'd really gain. I think this is a case where it's kind of like in the one-dimensional case, rather than doing a particle filter, you're probably better off doing numerical integration, because we can afford it usually in most applications. Optimal tracking is the right thing to use, I think, if you've got a one-dimensional state space problem. And similarly, if you're really just looking, if it's a unimodal posterior and you're just tracking the mean and the covariance, I think these sigma points are probably a better representation than what you get away with if you were choosing them randomly somehow.
So can we extend the sigma point filter, the unscented filter, to capture higher moments by adding more sigma points? Like, let's say I really want to know what my kurtosis is.
Yeah, I don't know much about that, but I think I've read that does exist, that people have developed algorithms that do go for those higher order moments. But I'm sorry, I don't know much about that. That's a great question. Other ones are too. So an example? So this is related to the application that Golriz described for homework 5, where we've got a quasi-periodic signal, and we're trying to track the frequency and track the coefficients of the different harmonics. And this in some respects is a little more advanced, and in some respects is simpler than what she presented. And later I had a PhD student that took this far further, that could account for amplitude modulation and frequency modulation, and was tracking more than one element. So this is a little simpler. So you all know that if you've got a perfectly periodic signal, it can be represented as a Fourier series, where you've got integer multiples k, in this case, of some fundamental frequency. And the way that it was represented in our early work, and what Golriz showed, is in a, what do they call that? The amplitude angle? That's not right. Amplitude phase form, I think is what it's called, where we had an amplitude on a cosine, and then it was some integer multiple of the instantaneous phase plus some constant that was the phase. And one problem with formulating the problem that way is that there's a really strong nonlinearity with that those other angles, with those phase angles for the different harmonics. When you're trying to use the Unscented Kalman filter or the extended Kalman filter, the more linear it is in the elements of the state vector, the better off you are. Probably the more accurately it's going to be able to track. And so we later started expressing this in the, gosh, I'm blanking on what the names are. There's 3 different forms of the Fourier series representation, and this is one of them, where instead of representing it as amplitude and phase angle, you've got a separate amplitude coefficient for the cosine and one for the sine. And so we later started representing it this way. It's still basically a Fourier series where we've got some number of harmonics, that's what that H is for, some number of harmonics that you're tracking, where they're harmonically related, they're all integer multiples of some frequency, but the way we're representing the amplitude and the phase are in terms of coefficients that are linear. And that's way better. And in fact, there's a way that you can combine the particle filter with the Kalman filter recursions if it's only nonlinear in a part of the state. And in this case, it's only nonlinear. The measurement model is only nonlinear in terms of the phase angle. And the only nonlinearity in the process model is in terms of the frequency. And so this is a really good example where you could actually put a particle filter together with the Kalman filter and track very, very well. I think it's called a marginalized particle filter, if I remember correctly. But basically, this is a generalization of a Fourier series representation of a periodic signal to the case where the fundamental frequency is changing over time. And if you look at this carefully, you'll see some things you recognize. The linear coefficients here that are unknown, AK and BK, that are being multiplied by the cosine and the sine, are following just random walk processes. This is very similar to the adaptive filter that we talked about before, where in that case we had a vector of the past measurements. Here instead, you've still got linear coefficients for AK and BK that are just following a random walk process, because the only information we have about these coefficients is that they're changing slowly over time. So the prior knowledge we're bringing to bear on this quasi-periodic signal, part of it is that the morphology of the signal is changing slowly over time. And I didn't express it in the slide, but we can also say, and we have no idea what it is to begin with. So we're going to track some kind of periodic signal. Maybe it's the heart rate, maybe it's an ECG signal, or a blood pressure signal. Or I had another PhD student that used basically this type of technique for tracking the pitch of bats that were doing echolocation. And they had, if you looked at the time frequency map of these signals, they look something like this. And there, of course, there was a second harmonic and a third harmonic, and et cetera. And these were at really high frequencies, ultrasonic. So this was like 80 kilohertz or something. And he was using this algorithm to basically track what were those frequencies. And once you've tracked it, then you could go back and use that to synthesize signals, where you could try things like, well, let's take out the second harmonic, and if we play this, see if the bats can still recognize what it is. You know, this was for communication rather than echolocation. Communication between, I think, a mother and poor baby bats. But in any case, if you've got a periodic signal where the frequency is time varying, you can take basically a Fourier series approximation where you've generalized it, so now the frequency can change over time. And in the applications we were working on, they were cardiovascular signals. So you had prior knowledge that, for example, if you were doing heart rate, it can't be any lower than some frequency and can't be any higher than some other frequency. This is one of the cases where I wanted to enforce some kind of constraints on what the estimate of the fundamental frequency could be, because I had prior knowledge on those constraints. And this is a relatively rudimentary way of doing it, where I simply incorporated it into the process model, which isn't quite right, because I'm adding the noise after the nonlinearity because I'm using the Unscented Kalman filter. If I had a particle filter, I could bring that inside, so that this limit would be strictly enforced. But with Unscented Kalman filter, I've got added noise, so it gets added after I've applied these constraints, and so they're kind of soft constraints in that respect. But some of the prior knowledge is there's some minimum and maximum, and I'm modeling this as an autoregressive process as well, not as a white noise process. There's an alpha here. So basically it's saying the frequency at time n+1 is related to what the frequency was at time n. It's not simply white noise, and it's certainly not a random walk. But in this case, it's fluctuating about some mean. There's some mean frequency. So, if it's my heart rate, maybe it's like 50 beats per minute. And if I've got that as part of my prior knowledge, I could put that in and say, yes, it's an autoregressive process, but with a non-zero mean. And this is how you can represent that type of autoregressive process with a non-zero mean. In later applications, we did make this, the mean frequency, one of the parameters of the state, and said this is going to change very slowly. We don't know what it is. Different people have different resting heart rates or mean heart rates. But that mean heart rate could also change over time. If you eat lunch, your resting heart rate may go up for a while as you're digesting the food, for example. But it doesn't change rapidly. And so we had a very slowly varying component and then much more rapidly varying component that we used to model the heart rate in that application. And the phase angle, the instantaneous phase, is just a straightforward approximation of an integral with no noise added. So you say basically the phase at time n plus 1 is equal to what it was, plus whatever the frequency uses to push it forward. TS was just the sampling interval.
So in this case, since you're basically truncating the PDF of the prior, right, with this soft minimum and soft maximum here, does that mean that, like when at the very beginning of the term we were talking about different ways of truncating a PDF, that you're going to have this region of higher probability to get the edges of what the frequency can be?
Yeah, this wasn't the most elegant way to do that. Given what I know now, if I was working on this again, I would handle this quite differently. Yeah, because the idea that if the frequency ends up being low enough that it bumps into that minimum, that's just going to stop there. Of course, that's not right. So there are better ways to incorporate that information. And what I read in the book in that last section of, I think it's chapter 7, that Aaron had pointed out last time, I think that truncated PDF idea would be a better idea. And I think there's probably better ways to go about this, but that was what we did. So that's the rationale. And I hope by showing this example also, this multi-dimensional example, it helps you maybe better understand something that's very hard for me to teach, which is how do you go about model design? We started off with an application where we were interested in tracking pulse pressure variation in children, basically how the amplitude of the signal varies with the respiratory rate. And then we started incorporating this idea, well, we know we can represent periodic signals a certain way. Can we generalize that? And how would we go about designing the process model? This isn't something that anyone gave us. We had to make it up and then defend that this was a reasonable model. And that's often how you end up developing these applications. Usually the measurement model is something reasonable, though there was design in the measurement model as well, because there's more than one way that is mathematically equivalent for representing a Fourier series. There's 3 different ways. But this one is the best for the kind of tracking that we're trying to do. There were good reasons for choosing that I went through before. So that's the kind of thinking that I look for in the projects and that I hope you take with you as we get towards the end of this class. So for the example I'm going to show you, these are the model parameters. And I'm sorry, I left one off, which is the mean heart rate, or the mean rate, and I don't remember what it was. It was probably 1, but I'm sorry, I just don't remember. I need to go back and update the slides where I list all of them. I try to be good about that. Most of you experience the frustration of reading a paper where people said, oh, we developed this tracker, and then they leave out critical information, so you can't even begin to replicate what they did. I think a number of you bumped into that. It's very common. We try very hard not to do that when we publish papers. And I skipped over it, but part of the problem definition was apply an auxiliary particle filter. It could have been anything, but I chose an auxiliary particle filter as well as the Unscented Kalman filter and compare the two. So we'll see a particle filter here as well. And if there's going to be a particle filter, then we've got some decisions to make, like what's your importance density going to be? And we chose the common choice of just using the process models of the prior. We only used, I only used 100 particles. Could have used more. And we're just going to be looking at the mean, because that's what the Unscented Kalman filter gives us, is really the reason for that. It's not that's necessarily more appropriate for this application. So this is really cool. This shows the frequency and the actual measurements we had to deal with. So we had a noisy quasi-periodic signal, and the true signal that we're working with is shown in red. The predicted estimate of that is shown in, I'm going to screw this up. There's 3 signals here, and I hope I don't have to correct myself on Tuesday. But I believe the red signal is before there's any noise added. The black signal is after there's measurement noise added. And the green signal is what the Unscented Kalman filter was predicting the measurement would be. So the predicted measurement is shown in green. And you can see initially the predicted measurement is kind of all over the place, it kind of gets small, and then it figures out what the frequency is, and it's finally able to start estimating the coefficients. And then after a while, it starts doing even better because it's able to lock on the coefficients to the second harmonic as well. It ends up starting to track that frequency well enough that about halfway through the recording, it's finally tracking really well. And you can kind of see that with a frequency that, in here, it's not matching very well because the estimate of the frequency is off quite a bit. So you can't estimate those coefficients when kind of the basis function is out of phase with actual measurements. But it doesn't take very long for it to finally kind of lock on to the frequency and start tracking the frequency accurately. And very, very shortly after it locks onto the frequency is when it's able to estimate the coefficients of the different harmonics, those linear coefficients, pretty accurately. You can see there's a lot of uncertainty initially. It's clear that the mean was 1, that this is fluctuating about from this plot. And you can see also that the UKF is lagging. When there's a change in frequency, the UKF lags a little bit before it comes up and tracks. It's a causal estimator. It's using the past up to the present, but it's not using the future. So you'd expect it to lag a little bit when there's a change in state for the tracker to be able to see that. You can see that here too, where it comes up a little bit in the estimator. It takes a while to come up, and it occurs again here. That's very typical behavior when you're using something that doesn't have smoothing in it. Any questions on these two plots? And yeah, I'm going to have to ask for your forgiveness too. I don't remember the green region, if that's plus or minus a standard deviation, 3 standard deviations, or 95% confidence interval. But because I wrote the code, I'm sure it's one of those 3. It's not something else, because I would only ever pick one of those 3. Just remind myself. This is a non-parametric spectrogram of the signal. And I've plotted the estimate of the frequency and the true frequency in red. So the true frequency is in red, and this gives you an idea. There's only, I should have specified this too, but there's only 2 harmonics. You can see there's nothing up here at higher frequencies. So this is the fundamental. The fundamental was stronger than the second harmonic a little bit. And again, you can see that initially it takes a while for it to figure out what the frequency is, but as soon as it figures out what it is, it starts tracking pretty well. And again, this is the signal that it had to work with. This is just an average across all time of what the power spectral density looked like. And this is the residual. I told you that the innovations are a great way of figuring out where there's problems, and this is a good illustration of that. And this was a key tool for us when we were tuning this to real data, when we were applying this to real data. And it's actually part of what led us to more and more complicated designs. When we realized there were sidebands, for example, above and below the frequency, we thought, we're capturing everything. We've got an amplitude modulation component in there. What could possibly be missing? Turned out we were missing a frequency modulation component that has different sidebands. So, and we saw that by studying spectrograms that are very similar to this. So if you look at this carefully, again, you can see the fundamental. It locks on to the frequency right about 12 seconds into the recording, and then it takes another 8 seconds or so for those coefficients to kind of lock in, and then it disappears, and you really don't see anything compared to just kind of the background noise that we see up here. If this was white, the whole image would look like this. The second harmonic took roughly another 10 seconds before it finally figured out what the coefficients were for the second harmonic and started tracking that, and then that disappeared when we were looking at the residuals. So this way of visualizing the performance was very effective for figuring out what it was really doing, where we didn't need to know what the true state was in this case. You can do this with real data because it's all driven by the innovations that I've been emphasizing. And then our old buddy, the auxiliary particle filter. Here's the estimate of the mean for the auxiliary particle filter. It does pretty dang well. Similarly, it takes a while for it to lock in, and once it locks in, you can see lags where the true frequency went up and the auxiliary particle filter comes up a little bit later. Or the true frequency goes down and the auxiliary particle filter comes down, but it takes a little bit of time, and of course there as well. Very similar behavior to the Unscented Kalman filter. And you would actually expect that. In the limit, is you get an infinite number of particles, the behavior of the auxiliary particle filter should match that of the optimal tracker. And if it's a unimodal posterior, then scented should be pretty close to that. So there shouldn't be a surprise that these two are similar to one another. This is showing 95% confidence interval just on the frequency, and you can see it's doing the right thing. I mean, I didn't compute it here, but it looks like roughly the state is out of bounds, maybe roughly 5% of the time, which is what it should be for a 95% confidence interval. Unimodal posterior, good indicator that the Unscented Kalman filter is a perfectly good choice for an application like this. There's nothing about this that would suggest that you would have a multimodal posterior, so Unscented is a good thing to use. And then this just shows a spectrogram with all three of them. This is the auxiliary particle filter. It doesn't quite dip down as much, and you could argue that it locks in a little more quickly, but again, this is just a single realization, so I don't think you would want to generalize that the auxiliary particle filter is able to lock in more quickly in general from this one recording. I think that's it on the example. So generally speaking, the Unscented Kalman filter is a really good tool. It's better than linearization. It's just as fast as the EKF. It's much more efficient than a particle filter. It's good for real-time applications, and you don't have to worry about these Jacobians. There are some disadvantages. You know, it assumes you've got additive process and measurement noise. There are ways to circumvent that, but at the cost of more computation. And again, the convergence proof I think is a little bit weak. I don't think you can really say anything about optimality, even asymptotically. I don't think there's any kind of asymptotic result we can claim any kind of optimality for the Unscented Kalman filter. We could for basically every other tracker we've talked about this term has some kind of optimality, but the Unscented just doesn't, unless it's linear, in which case it's kind of silly because you should be using the Kalman filter. And Unscented just becomes equivalent to it in the linear case. And it's only tracking the second order statistics, so compared to particle filters, that's a weakness. If you've got any reason to think you've got a multimodal posterior, you really probably ought to be using a particle filter. And I think that's it. So I will, for Tuesday, I will circle back and add the car tracking example, because Walt asked for it, and I'm curious to see it too. I want to see what it looks like. So I'll add that in. And the one of the slides, I'll give kind of an overview, and I'll go through some more case study examples of tracking, and hopefully give you some more tips about how to work with the different algorithms we've talked about this term on Tuesday. And I'll say a little bit more about the final quiz, but not much.
You'll expect us to say a lot about the final quiz.
Yeah. Well, I expect brief responses. That's faster for me to grade. But yes, you'll probably be seeing more than me.
So you mentioned that if we suspect the posterior is going to be multimodal, to use a particle filter instead of the unscented.
Yeah.
But how would you know to anticipate that, I guess, before
Yeah.
a particle?
Well, part of that comes from having a deep understanding of your application. And really that's about a deep understanding of how your measurements are related to your state and how your state changes over time. And usually from the application, if you say, there's an ambiguity, not an ambiguity where the state, I may not have a very good estimate of it at certain times because the measurements aren't related, or I'm missing measurements at certain times, but there's an ambiguity where it's possible that the state could be in one of two very distinct places and not in between. So a soccer ball example, where you're tracking the soccer ball, it's going to be in some number of very distinct locations when it's based on detecting edges in an image like what Aaron showed us. If you're tracking something with an array, and you're kind of beamforming and you've got range and bearing estimates, which I think is related to the application you're working on, then there's less reason to think that it's going to be bimodal. Although there was someone from the Near Lab that did a really cool application where there was a river, and something was moving through the river. I forget what it was, but there was an object in the river. And so when the object was moving down and you looked at the posterior, it split when it went around here, because it was possible that the state was going to go to the right or the left of the object, but you didn't know which. And so for part of the time when the thing that was being tracked was moving around that object, there was an ambiguity where it had to be in one of two places. And who knows what the Unscented Kalman filter would do with this. I don't know if it would create a single mode that's really wide, or if it would pick just one of those. But in something like that, it's in one or two places, and your measurements may be ambiguous, so it's going to be multimodal in that case. So often you have that kind of knowledge. We were tracking the car going around the track, and there's certain times where you can't quite tell if it was going backwards or forwards, but you know that it had that it was no longer on the edge. And so again, from just that knowledge alone, that's enough to know that it's going to be multimodal. So often, by really studying, especially the measurement model, and understanding, how do the measurements relate to the state? Is there a possibility where it could be in distinct places but not in between? Then that can often lead you to know. The other thing you can do is just try it with a particle filter. And I know that can be more trouble because it takes time, but you can do the particle filter and then look at, for each dimension of the state, look at estimates of the posterior. It doesn't give you the full picture because you're trying to look at a high-dimensional PDF and you're just looking at these narrow slices of it in a single dimension. But that nonetheless can give you pretty good evidence as to whether it's multimodal or not.
I can't help but mention how that example, it reminds me of the double slit experiment.
Yeah.
So if you don't observe which way it goes, then the posterior has two modes. But if you did and you knew it went through one, then there's just one mode, and it's kind of analogous to...
Yeah, it is. You're right. Yeah, nice. Okay, well, we'll end there today. Good luck with working on your projects, and have a great weekend.